Welcome back to the Math Professors. Our YouTube channel covers topics that can be found in any college math class. I'm Professor Van Hamlin, and we're going to cover some Taylor series today. In particular, centered at a equals 0, which is really the Maclaurin series. So the Taylor series, f of x can be written as f of a, f prime of a times x minus a, f double prime of a all over 2 factorial times x minus a squared, f triple prime of a over 3 factorial, x minus a cubed, all the way up to the nth derivative of a, all over n factorial, x minus a to the n, and then so on forever and ever and ever. So really what a Taylor series does is it takes a function and turns it into a power series, which you can kind of think of it as like an infinitely long polynomial. So the Maclaurin series is this thing centered at a equals 0, so this would be f of 0, f prime of 0, x minus 0 to the first power, and then so on. You guys can see that all I've done is just plug in a equals 0. So what I want to do is I want to determine the Taylor series of e to the x centered at a equals 0, or really the Maclaurin series of e to the x. So let's turn e to the x into a power series. So in order to do this, it comes down to us being able to find, the function, its derivative, its second derivative, its third derivative, and so on, all the way up and see if we can get like a pattern for its nth derivative. And then we'll center it at a, which means I'm going to plug in a equals 0 into the functions and its derivatives, so that I can find really kind of the coefficients, well, the numerator of the coefficients. So let's start. So let's start out with f of x, which is equal to e to the x, and then I'm gonna have to find all its derivatives. So f prime of x. One nice thing about e to the x is it's still e to the x. F double prime of x is still e to the x. F triple prime of x is, e to the x. And what we can see is I've chosen a nice function because its derivative, regardless, so the nth derivative of x is still going to be equal to e to the x, and and so on. Now remember, I want to center this at a equals 0, so what I'm going to have to do is I'm going to have to plug in, 0 now. So f of 0 is e to the 0, which is going to be equal to 1. F prime of 0 is going to also be e to the 0, which is going to be equal to 1. So we can see that all these at 0 is going to be equal to 1. So now I have, the numerators of all these coefficients. So what that means is I can rewrite our f of x, or e to the x, as, f of 0, which is going to be equal to 1, plus f prime of 0, which is also going to be equal to 1 times x, plus f double prime of 0, which is going to be 1 all over 2 factorial x squared, plus now f triple prime is going to be 1 over 3 factorial x cubed, plus, and then so on, all the way up to this nth term, which is still going to be 1 all over n factorial x to the nth, plus, and so on. So when we don't have to simplify it much, but 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, x to the fourth over 4 factorial if we just consider pattern, all the way up to x to the n all over n factorial plus, and so on. So what this means is I can write this thing as a summation. So another way to write this is going to be the summation from n equals 0 to infinity of x to the n all over n factorial. So this is equal to e to the x. Now what I want to do on top of this is talk about how we can find the derivative of this and also the integral of this using its power series, and we know its derivative and its integral already. So let's make it look nice. So what I want to do is I want to use this power series to be able to find its derivative and also its integral and really verify that you still get e to the x back. So what we know is the derivative with respect to x of e to the x should be equal to the derivative with respect to, this sum. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on, x to the n over n factorial. So when I take this thing's derivative, well, the derivative of 1 is going to be 0. The derivative of x is going to be equal to 1. The derivative of this, the power is going to go in front, so this is going to be 2x all over 2 factorial plus, 3x squared over 3 factorial plus 4x cubed over 4 factorial for that one, plus, well, what happens here is for the nth term is the n is going to go in front. This is going to be x to the n minus 1 all over n factorial, plus and so on. So what we can see is when I simplify this expression, this is going to be equal to 1 plus, well, 2 factorial is going to be 2 times 1, so the 2 is going to cancel, so this is just going to be x. Now, similar here, 3 on the numerator, I have 3 times 2 times 1, so the 3 is going to cancel, so this is going to be x squared all over, well, 2 times 1, which is 2 factorial, plus... the 4's are going to cancel, so this is 4 times 3 times 2 times 1, so this is going to be x cubed over 3 factorial, and then so on, plus this is going to be x to the n minus 1 all over, well, this is n, and on the bottom I have n factorial. Well, n factorial is equal to n times n minus 1 times n minus 2 times n minus 3, all the way till I get to 3 times 2 times 1. So one way we can write n factorial is n times n minus 1 factorial, because n minus 1 factorial is going to be that. So what's going to happen here is the n's are going to cancel, so this is going to be an n minus 1 factorial. So our goal really is to talk about this. Well, if I want to integrate this in this summation notation, we can really just take, sorry, not integrate, but take its derivative. So the derivative with respect to x of e to the x is going to be equal to the derivative with respect to x of this summation from n equals 0 to infinity of x to the n all over n factorial. Now what we know is going to happen here is this n is going to go in front, so this is going to be equal to the summation from n is equal to 0 to infinity of, well, this right here. X to the, oh, we got to be careful of the index, x to the n minus 1 all over n minus 1 factorial. Now, the reason I left the index blank is I want to kind of talk about what happens here. Well, the first one, we know that this is going to be the summation from n equals 0 all the way to infinity. Now, what happens to the summation is, since the first one turns into a 0, it now starts here. So it started at n equals 0. It's now going to start at 1 over, which is going to be n is equal to 1. So one way we can write this is now the summation from n is equal to 1 to infinity of x to the n minus 1 all over n minus 1 factorial. Now, it doesn't really look like this exactly. It's pretty daggone close. So what I'm going to do is I'm going to re-index this so that it looks exactly the same. And by doing that, what I'm going to do is I'm just going to plug in, let's let n equal n minus 1. So I'm going to stuff in, n plus 1. I'm going to stuff in n plus 1 into all these n's. So all these n's right here, I'm going to substitute for n plus 1. So this is going to be the summation of n plus 1 equals 1 to infinity of x to the n plus 1 minus 1 all over n plus 1 minus 1 factorial. And what we can see is when I solve down here, we're going to have the summation of n equals 0 to infinity of x to the n all over n factorial, which we know is e to the x. Now let's do its